Hi, welcome back. From the analysis of linear time-invariant systems came this mathematical operation called convolution. This is just a mathematical operation, and just like other mathematical operations, it has some properties to it that we should be aware of that will help us perform these convolutions. So think about, for example, multiplication is a mathematical operation. There are some properties that we know of about multiplication. Addition is a mathematical operation. There are some properties that we know of about addition. So let's take a look at these properties of convolution and how they can help us. So first of all, speaking of multiplication, it has an identity property. Okay, the identity property of multiplication, that says that 1 times, and x is a number here. 1 times x is just x. So the number 1 is the identity of multiplication, right? And there's also an identity property of addition. It says 0 plus a number gives me that number. And here 0 is the identity for addition. Okay, it turns out that there is an identity property of convolution where some signal convolved with any signal gives me that signal back, right? So what signal do you think that is? And that would be the identity signal of convolution. What signal do you think that is? Pause the video if you want to think about it. And to answer that question, let's remember how we got here, how we got to convolution, right? If I have a linear time-invariant system and I put in x, then the output is x convolved with its impulse response. This is true for any x. So let's strategically pick an x. Let's pick the delta function. And what do I get out when I put in the delta function? Well, by definition, I get out the impulse response, the response to an impulse. So here we have it now. We have the delta convolved with some signal. That gives us that signal back. So it's the delta function that is the identity of convolution. And from time invariance, a much more strong or general property holds that if I shift an impulse by a constant and I convolve it with a signal, I get out a shifted signal like that. Okay, and the same thing follows, or a similar thing follows in discrete time. This is the identity property of convolution. Okay, next. It turns out that convolution is commutative. By the way, before we get to commutative property, going back to the identity, so if you need to convolve something with an impulse, well, you should welcome that, because it's like multiplying by 1, so it's very easy. So you should leverage that if you ever have the opportunity to convolve something with an impulse. You should take advantage of that. Okay, back to commutative property. So I'm just going to prove this. Xn convolved with Hn. I'm going to prove the commutative property, and just so you can get a flavor of how these proofs work, I'm not going to prove all of the ones that you'll see in this video, just this first one. So by definition, x convolved with h, I have it up here in the box. This is k goes from minus infinity to infinity, x of k, h of n minus k. All right. Now, I'm going to let, this is a change in variables, some other index r equal n minus k. We used a change in variables in one of the discrete time convolution examples. Basically, I can call the index whatever I want, and I'm going to try to get rid of k. My cat is in the room right now, so you might hear him meow. But I'm going to try to get rid of k, and when k is minus infinity, n plus infinity is just infinity. So this is r equals infinity. And when k is equal to infinity, this is n minus infinity. So r is minus infinity. So like that. And then if I solve for k in this little equation that I've set up, k is n minus r. Like this. And then h is r. This is h of r. Like this. Now, this becomes, well, first of all, I can switch the order of summation without changing the summation. And briefly, the reason I can do that, if you want to think of a geometric series like 1 plus 1/2 plus 1/4 plus 1/8, it doesn't matter if I add the numbers up that way or if I add them up 1/8 plus 1/4 plus 1/2 plus 1, because addition commutes. Then, because multiplication commutes, I can switch these guys. I can switch h with x like this. Okay, and now I compare that with my definition of convolution, and you see k is replaced with r, but I can call the index whatever I want. But you see the x and the h have switched roles. You see that? So this is h convolved with x, like this. So that's the proof. X convolved with h is the same as h convolved with x. That means when we're calculating these convolutions, I can choose whichever one I want to flip and shift. So I'll choose the easier one, the simpler one, to flip and shift. And by the way, in continuous time, this also applies. That x convolved with h is h convolved with x. The interpretation here is that if I have x of t as input to an LTI system with impulse response h of t, of course I'll get out y of t, but that's the same situation then as if I put in h of t into a system with impulse response x of t. I get out the same thing. That's the interpretation behind the commutative property. Okay, next. Convolution is distributive. Okay, so let's say I had a signal. I'm just going to draw it in continuous time, but this applies for discrete time as well. And I sent that signal to an LTI system with impulse response h1 and separately h2 of t. And then I added the outputs, and that made y. Okay, this is a parallel combination of two systems. So I might ask, well, what's the impulse response of the overall system? So the overall system is like this thing here, right, where I input x and I output y. Well, to get the impulse response of the green box, plug in an impulse into the green box and observe what you get out. What you get out is literally the impulse response of the system then. So we don't know yet. Okay, so if I plug in an impulse, then the impulse comes up here to H1. So what do I get out? Well, I get out the impulse response, of course. And what do I get out down here? Its impulse response. Then those two are added together, so what I get out is the summation of those two things. So this is the impulse response of the whole thing. Okay, so the distributive property then says that this situation is equivalent to one system whose impulse response is H1 plus H2. And so in this one system, I would have X1 comes in, convolved with the one system's impulse response. Right, that gives me Y of t. Okay, and then the top picture says, that shouldn't be an X1, by the way. That should just be an X. So that's the bottom picture. X comes in, we convolve it with the impulse response of the box, and then we get out the output. Then the top picture says that X goes to the top, and then that output is added to when X goes to the bottom. Of course, we know that as the distributive property, the X can be distributed inside the parentheses. And so that's the interpretation, though. These two circuits or systems are equivalent systems. Okay, I'm going to erase that. And the last property, what do you think? Convolution is associative. Okay, let's remember association. I'll write it out in continuous time, but it also applies to discrete time. So I can, if I have three convolutions, I can choose which two I'm going to convolve first. So I can move the parentheses around. In other words, I can associate H1 with H2, or I can associate X with H1. Right? Those are the same things. So I'll write it out for discrete time as well. Just to emphasize that it does hold in both cases. Okay, and the interpretation is this. Let's say, and I'll just draw it for continuous time. Let's say I have an input to a series of two LTI systems with impulse responses H1 and H2. Okay, it turns out then if the associative property holds, which it does, I can switch the order of these two systems. and get the same thing out. So let's understand that interpretation. In the first picture, I have x, and then what do I get out of the first box? Well, x convolved with h1. Okay. Then that's the input to the next box. So what do I get out? Well, that convolved with h2. That's what I get out. Right, and then this picture down here, I have x convolved with h2, then convolved with h1, and that gives me y of t. Okay, so that's the associative property. So you can use these properties then to help you manipulate the convolution. Use the identity property if you have any impulses, use the distributive property if you need to, or the associative property, and use those to your advantage.